Hello, welcome to another video. For this video, we're going to talk about Chapter 9, which is Periodic Properties of the Elements. In the beginning, though, we're going to reference a little bit from Chapter 8. We talk about electron configurations. So just as all the others, make sure before you start that you have a copy of the handout for the guided notes that go along with this video so you can follow along with all of the example problems. And I've also included a couple additional printouts for you as well. So this video, you'll also like to have this periodic table that shows the electron configurations and where they are in the different blocks of the periodic table. So there's this one, and then there's this copy that's also color-coded but has the additional information here on the top that shows you how many electrons fit in each of those sub-level areas of the blocks. And finally, the last page of that second document has this graphic as well that kind of overviews everything that's going to be discussed in this video with notation, a handy guide to filling order that's also written out linearly at the bottom. So check those out, and that will help you follow along. Now, with that all the way, let's get into it. So first thing we're going to do is do a very short review on atomic structure. We've kind of deviated from that since the beginning of the class. And so here we have the scientist Rutherford, and it was his experiment with the gold foil that was able to give us that picture of the atom is not a solid sphere as previously thought, that the actual atom is mostly empty space, and the center was the most dense positive portion of the atom, which we then located the nucleus. Then we got to scientist Niels Bohr. And so Niels Bohr is taking that Rutherford diagram a little more detail, and what we see here is his planetary model of the atom. And so it's called the planetary model because it looks like a little solar system there with the electrons being planets orbiting around a nucleus that would be like a sun. So with this, we're able to see that electrons are in these different energy levels, these paths, and it's not quite as simple as the diagram looks, where they're equally spaced out and completely circular. We will see that in the video today. But this is just an introductory step to get you to view the atom in a way that's going to be helpful for looking at those little electrons. That's what we're going to focus on here. So looking at Bohr's model in a slightly different picture here, we can see the energy levels. And so they are numbered with the letter N. So the first energy level is the closest to the nucleus. The second energy level would be the next distance away, and then the third, and so on. And in this picture, we can see that electrons are able to move. This explains things that glow. So I usually do that as a demo in the high schools. I will take glow sticks and pass them around, and we kind of, really examine the glow stick and see, how does it work, and start thinking about it, because usually kids will just crack them to get them activated and not think about it, right? But essentially what's happening is what you see on the screen here. When you crack the glow stick, it causes two chemicals to interact, and there's a reaction. And with that reaction, you're exciting the electrons of one of those chemicals, causing them to jump. Now, things like to be at a low energy state, so causing that electron to jump was an increase in energy. It's going to want to then fall back, as we would say, to give that energy back. And when it does that, the energy that's released is slightly different in wavelength, and it would happen to be in the visible spectrum. So this is why we're able to see some color with something like a glow stick. So that's an example of this being applied to something every day. And so here's my glow stick. So the quanta, or quantum for plural, is, sorry about that, is the amount of energy required to move an electron from its present energy level to the next higher energy level. Sorry, the picture there is stuck in place, and I'm not able to move it right at this moment. But you could just pause the video and go back to where I just read it to you all. So the quantum mechanical model is taking Bohr's model and becoming even more detailed. As we got better instrumentation, we were able to do more detailed experiments, and we were able to find out even more about atomic structure. And so this is by Erwin Schrödinger. Yes, that Erwin Schrödinger, where the mathematical equations that are way beyond the scope of this class describe the different locations and energies of the electron. Electrons are not in those definitive paths that Bohr hinted at with his planetary model. And so we're going to see the results of Schrödinger's work here in studying the different areas and how they are different from each other where these electrons can be found. Okay, how electrons orbit nuclei. And so we see in the top left corner there an image that is representing Bohr's atomic model. But in actuality, instead of seeing these concentric rings, what we're seeing is these different shaped paths where the electrons can be found. Now notice the nuclei are in the center there. Okay, so there's our nucleus, and we see the electrons kind of coming out in this balloon shape. Well, all that is a probability diagram of the mathematical equation that Schrödinger had worked up, giving us the highest probability space of where to find an electron at any moment in time. So electrons move extremely fast, and so we can't take a picture of them in that moment. And so the best we can do is say there are electrons in this area around the nucleus at X number of time. So we can give a probability map, and that's what you're seeing on the screen right here. So we need to get through some definitions. So we have an atomic orbital. This is the region in space where the electron is likely to be found. So going back to that probability basis here for this model of the atom. Okay, here we can see a different picture. This is of a hydrogen atom. And let me just see if I can pull the screen down just a tad. Okay. I don't think that's going to stay in focus there. Sorry about that. So it's just getting cut off at the bottom of the screen there. So a quantum mechanical model of hydrogen. Hydrogen is the smallest atom, so it's the simplest one to study for something like this, to just get what one atom, one electron would show. And here we're seeing the likelihood of finding an electron in that region. So notice how very dark the image is towards the center of the picture, the center being where that nucleus would be. The electron would be very close to it. Let's go back to charges. So the nucleus, having protons, is a positive charged entity of the atom. The electrons, which are outside of the nucleus, are negatively charged. So, like the saying says, opposites attract. The electrons and the protons of the nucleus are going to kind of keep them in place. And so we see the electrons being very attracted to the center where the protons are, and then that probability map starts to fade as we go outward, because the probability of finding electrons decreases as we leave the nucleus region. Okay, an energy level. So an energy level is that largest space where we can find an electron. You see an image of some data there, what this looks like if we were in a lab. We do not have the capability of doing labs like this, sorry to disappoint, but there's plenty of YouTube videos if you really wanted to look into it. The energy level is much like the town that you live in, the town address. And then we're going to get more detailed from here. So right now we're going to start at the town level, and that would be our energy level. These are equal to the period where we find an element on the periodic table. So we'll go through examples a little later on, but if we locate any element, the period that it resides in, it's going to tell us the maximum number of energy levels that atom will have. Okay, so more on that in just a moment. A sublevel would be like the street address that's in your town. So we've gone from the town energy level to the sublevel, which is like your street address. It's more specific, right? So the sublevel, they have letter designations, S, P, D, and F. Those used to stand for particular terms, but later were discovered that the terms that were originally used did not apply to what the data was showing as data got more specific with this. So the initials were kept, but the terms were not. So this describes the shape of the orbital where we find these electrons. So this is within an energy level, we have these different sublevels. Here's just a small offering of what the different ones can look like. So I know it's a bit grainy, but the top picture shows two different s orbitals side by side, and then we can see the p orbitals. I'll go into more detail in just a moment. And the bottom shows 5 variations of a d orbital type. So here we see a more detailed image with the s orbital. Notice it's a sphere. So that is what the s originally stood for. The other terms that you're going to see for the next few sublevel types in the sequence, they will be ways to remember the shape, but they are not the original terms where the letters derived from. Okay, so S, you could think sphere, it's just that spherical shape sublevel. Okay, so this is a p orbital, and for that, you can remember it's a peanut shape, so I put Mr. Peanut there. So we can also call this a dumbbell shaped if we think about weights, right? It's got the large ends, and then it kind of gets skinnier in the middle. And what you can notice here is that we have 3 different variations of the p orbital, and if you look at the axes, all it is describing 3 dimensions in space. And so I have a couple models here to help you visualize that. Okay, so if the first one, if we look at it, it's along the x-axis. So let's say that this model here, that's purple in color, let's say that the white is the nucleus here, and the 2 p orbitals, notice that they're on either side. So it's using almost a figure-8 pattern around the nuclei, going to each of these parts of the p orbital in order to have that electron constantly moving. So this is along the x-axis, okay? So looking at the next picture, we see it along the y. And so if I were to do that with this model, okay, we're used to seeing the y-axis as up and down. So this is a separate p sublevel, okay, separate p sublevel, I'm just trying to line it up there, with the nucleus, okay, so we'd have 2 electrons spinning around in this location, and we'd have 2 electrons spinning around in this location. And so that would be 2 dimensions, right? But wait, I'm going to try to hold these together and bring in my z. So the z-axis that makes it 3-dimensional is where we'd have one lobe of the p sublevel coming out at you and one lobe facing away. So it's coming into the camera like that and out. So I'll just tilt it slightly. So it's coming in and out of the screen in 3 dimensions there. And so those are the 3 separate orbitals of a p sublevel. I know, it's very wordy, right? So the orbitals are like your house number of your street address, which we're going to cover in a second. Okay, D sublevels can come in 5 variations, and so as you see here, we have our schematic for 3 dimensions, x, y, and z axes again, but the image gets really twisted up, especially if you look at that image on the far right. And so that's where the donut comes in. The other ones you could think of daisies for D, right? Another way is clover, but that doesn't start with a D. But they look like 4-leaf clovers, right? So this would be one orbital, just like this one model was one orbital for the p sublevel. Each of these 5 are individual orbitals that together make up the d sublevel. Okay, and so you can have any combination of these. You don't have to have all of them for a d sublevel to be there. So we're going to see that soon as well. Finally, F is all over the place. So we can call that fancy. And I'll just move my picture for a second. So we can call that fancy for F. It used to stand for fundamental, but as you can see from these images, it is no way near that. We have some space here where it's not being directed towards the nuclei like we saw in the P and the D. It gets really tapered as we get closer to the nucleus there to show that higher concentration, that higher probability of finding an electron there. Here, we don't see that in these top images. There's almost a gap there. And then we see many more of these lobes, I'll call them, that make up these orbitals. Remember, each of these are an individual piece. Together, all of them make up the F sublevel. Okay, sounds complicated so far, but it's not going to be too bad because the periodic table can be a map for us to navigate to different elements and find out how many sublevels are there, how many energy levels are there, and so on, and where to place these electrons. And so again, I'm just going to reference you to where I started in the beginning, having at least one of these periodic tables that I've added to the notes file that you're able to have these out. This might be a good one to start with because it's going to help you see how we count across the blocks of the periodic table and discover whereabouts we are as far as energy level and sublevel and so on. So we have different blocks. So let me just move my picture again, blocking helium there. And so the S sublevel is found when we encounter elements located where you see highlighted here in that kind of salmon color. This is called the S block. Now helium is over here because it behaves chemically like a noble gas. So it's placed with 8A. But if we go back over here to the left where we see the majority of the S block, we can see that helium would fit in this little cutout next to hydrogen. It's not there because helium does not act like an alkaline earth metal, which is this group of elements. So just keep in mind, helium does count, but it's way over on the other side. Okay, so after the S, we have this other area. Notice how the periodic table shape helps you see where this block is. So it kind of rises up here towards helium. This is called the P block. And when we encounter elements or go through this section, when we're looking at a way to address all of the electrons, which is what we're going to be doing, when we go through this area, we're in the P sublevel area for those numbers of electrons. It'll make sense, I swear. Okay. Next, we have D. So D is in the very center where our transition metals are found. You want to notice that they are 10 blocks wide. Okay. The S are 2 blocks wide, and the P is 6 blocks wide. Okay. That's how many electrons can fit in each of these in a maximum capacity. If you go back to this handout that I've included, this is all in this center box here. So it'll say how many sections there are for each color, for each sublevel, and then that translates to how many electrons that will be held in that sublevel. So finally, we can't leave out F, right? The F sublevel is the inner transition, or the rare earth metals, down here at the bottom. And so you'll notice that that is 14 boxes wide. Okay, so this is all going to be pertinent in just a moment. Okay, so how electrons orbit nuclei. The third thing to mention here would be the spatial orientation of the orbital in space. And so this is what I had talked about when I had the model kits, and I showed you the X and the Y in 3 dimensions here with my Z. how these all line up. And so that's what we're talking about. The spatial orientation is just how it's taking up three-dimensional space. And so that's why it's referring to X, Y, and Z axes here. And then if you've had some higher maths, you would definitely see how these would relate to higher dimensions, but we're not going to talk about that. Okay, and so I have an image here to kind of help you see that plane. I think the model kit did a fairly good job as well. Just kind of hide myself up here. Okay. Another thing we need to talk about is as the electrons are orbiting in these sublevels, in these orbits, they also have to be paired up in that sublevel. So, for example, if we look at just the x axes of a p sublevels orbital, I know lots of vocab, okay? This is just one orbital of the p sublevel. It's along the x-axis. This can hold a maximum of 2 electrons, and they will be moving in, like I had mentioned prior, a figure-8 pattern, but also the 2 electrons are going in opposite directions of each other. This is because the electrons are both negatively charged, and if they are going the same direction, they're likely to encounter each other more often, and if the same charges come near each other, they're going to repel. That's not going to keep our atom together. So the same charges want to spend the maximum distance away from each other. So they are going to go in opposite directions. One will go a figure-8 in one way, one will go a figure-8 in the other way for a p sublevel. And so that's what this image is showing here. We will be drawing this in a little while. Okay, an electron configuration is where this all ties in together. What we're going to do next here is we're going to give a address. Just like I had mentioned earlier, the energy level is like your town, the sublevel is like your street, and then the number of electrons in that orbital would be like your house number. So we're going to give that specific address to each electron of an atom for an element. Sounds like it's going to be very, very intense because we know the atomic number is the number of electrons. So some of these atoms are fairly big, right? We're going to give an address to every electron. Hold that thought because it does get a little easier when we organize it. We're not going to write, you'll see, we're not going to write every individual electron. We're going to group them like we see here. Okay, so if we look at the element sulfur, go ahead and find it on a periodic table. It doesn't matter which one. I would suggest starting out to use this periodic table since the width of each sublevel block is pointed out to you and labeled so that we can follow along here as we get started. So where is sulfur? Sulfur is right here. Okay, so what we want to do is we want to give an address to all 16 electrons that sulfur has. Not all of them are in the same energy level. Okay, it's going to go in a certain order, and every element is done the same way. Okay, if we look at the screen here, what you see in front of you, the 1s2, 2s2, and so on, is giving an address to all 16 electrons. That's called an electron configuration. The location on the table where you can find that particular element is given by the last part of the address. So we need the entire configuration for the element sulfur, but a way to use the periodic table as a map, I could provide just the last bit. So I'm giving you an energy level, 3. That tells me I'm in period 3. The P as a sublevel, that tells me I'm in this block of period 3. And finally, the superscript of 4 tells me how many boxes in I go. So aluminum would be box 1, silicon would be box 2, phosphorus would be box 3, box 4, I land on sulfur. So we can also use part of the electron configuration, that last part, that ending, to be a location of an element. So this is something that would show up in like a multiple choice question, for example. What would be the location of sulfur with its electron configuration ending? Okay. The rest of it are the directions. So how do we get to 3p4? We have to go through all of the energy levels, so we're accounting for all of sulfur's electrons. Okay, remember there's 16 electrons for sulfur, and so we need to give an address for all of them. So there are 2 in the first energy level, there are 8 in the second energy level. See the exponents or superscripts here? The 2 and the 6 would be added together here because the energy level is the same. We have 2. It's broken up into different shapes, but they're in the same energy level. I might be getting ahead of myself. Let's take a look at this. So this is the notation basics for what each part means in an electron configuration address. So that exponent or superscript is going to tell you the number of electrons at that location. Okay, so it's important you know this. The first number in front that's written really large, that tells you the energy level you're currently in. And lastly, the letter, which is written as a lowercase, tells you the sublevel. So you can see, taking all of these pieces together, it's giving me a specific location. It's telling me the period I'm in, the energy level, the sublevel block of the periodic table I'm in, and then how many boxes to count over in that sublevel, that's equal to the number of electrons. Remember, as I count boxes, my atomic number is increasing by 1. So that means my number of electrons for the atoms are increasing by 1. That's how we're able to use the periodic table to do this skill, because of it going in a sequential order for electrons. All right, so now the notes are a little different format here. We don't have as much for you to write, really. I have a lot of animations in this particular one to help you see, through the computer screen, what I'm trying to teach. So let's take a look at the first one. We're going to start with hydrogen. Okay, so I have hydrogen highlighted up here in the periodic table. It's our first element. So we only have 1 electron to give an address to, but it's a way to start. So the way to go through one of these, you'll become very fast at it once you get the steps down. But very initially, in the beginner level, we want to note a few things about the element we're asked about. What's the atomic number for hydrogen? What's the period that hydrogen is in? And then what block, the color coding, what block is hydrogen located in? And that's kind of getting your start with doing an electron configuration. So again, hydrogen's the smallest element. It only has 1 electron, so its atomic number is 1. The period is also 1 because it's in the top row. And it's in the S block because, again, the S block is the furthest over to the left on the periodic table. So we've established this. And so the period is 1. That tells me the energy level. So I can write a large 1 to start my electron configuration. Then we said that the block was S. So that's written next. Now, I just want to clarify something. So shells is written here. I tried to correct all those. I must have missed this one. Shells and electron energy level are equivalents. So it's a preference, or perhaps however someone was taught, whether it's an author of a textbook or myself. I was taught with energy level, but there are, documents and activities and books that will call them shells. So just know that if I say shells or energy level, they're the same thing. Sorry to throw another vocab word in there. But this is equal to the period number, right? I'm pointing at the 1. Okay. The letter tells me the orbital or block it's in. Hydrogen, we're looking at just hydrogen, is in the S block. And then how many electrons are there? Hydrogen only has one electron, so that would be the superscript here, or exponent, which is a 1. So altogether, hydrogen having just one electron to give a location to, we would say the configuration is 1s1. That's how this would be read. So on this periodic table, it's similar to the one I've been holding up, where we're going to track a few examples here, and we're going to go across the periodic table. Let me just scooch my video down just a little so you can see the top part. Okay, notice that helium over there in the top right is still 1s. It's in period 1, so it's still 1, and it's part of the s block, because the s block, if you look at all the other periods, is 2 blocks wide. So we would say that the s sublevel can hold 2 electrons maximum. Remember, each block is 1 more electron as we read from left to right. So going from the first group, group 1A, that first column on the left, that's 1 electron space. And then if I go to the next column, group 2A, that's the second space for S. So it's holding 2 electrons for S. Then you can see we would go left to right. If I'm in period 2, I'm going left to right, skipping over the center portion. There is no portion of the D block here in period 2. Okay? So I would just keep reading left to right like I'm reading a book, and I end up in 2p next. Okay, so that's kind of the style we're going to go with. So let's go to the next element. Let's look at helium. Okay, I didn't put all of these examples in the notes because I thought it would be a lot of redundancy, so you'll see that this one's not in your notes, but let's just go through it together here. So helium is in period 1. It's also part of the s block. Its atomic number, however, is 2. So helium's atomic number is 2. We only have 2 electrons to account for. The s sublevel can hold a maximum of 2 electrons, so they're all going to be located here. Helium's electron configuration would be read as 1s2. Okay, and here it is. So next, I think this one I put in the notes here. So this one is lithium, atomic number 3. Okay, so it's atomic number 3, but we're in period 2. So we need to account for all 3 electrons. Okay, so take a look what we have on the screen. I just put a bunch of stuff up. Let's go through it together. So I have to account for all 3 electrons. If you add up these exponents, superscripts, okay, I'll call them superscripts here because they're not functioning in a mathematical way, an operation like an exponent would. So let's say the superscripts here, they represent the actual number of electrons that are at that location. So in theory, we should be able to add up all of these superscripts when we're done with a configuration and get the atomic number, right? That's the total number of electrons, and we're accounting for each one of them. So this turns out to be a way to check your answer when you're doing electron configurations. If we add up all of these superscripts and we don't get the atomic number, something's wrong. This always works. Okay, so it is a check for you. So what do we have to do? We have to go through the periodic table when doing these as if it's a map. So let's say that the only entrance to the place where this map represents, I used to talk about it as a mall. Malls are becoming less and less abundant lately. So, but if you recall the old days of malls, we could still use that scenario here. So this is your map of the mall. It only has one entrance though, and that's hydrogen. You have to start at hydrogen. And there's only one way that you can walk. So it's no wonder the malls aren't around anymore, right? So you have to come in hydrogen. You have to walk all the way across till you hit helium. Then you can drop down to the next level, just like reading a book. Then we're going to read the entire left to right of that row. Then we're going to drop down again. We're going to read the entirety of that row, and so on. And so this is how we're going to account for every electron for any element. So as we're reading along, if we end up in a new block, we have to write that. If we end up in a new energy level, because we had to drop down for lithium, it's in period 2, we have to show that. That's the configuration. So what I did was I started at hydrogen, that's my entrance, and I said 1s1, counting the first electron for lithium. I then continued in the period to helium. This is 1s2. Let me go back for a second and just point out that notice I only wrote when I was full with 2 electrons in that S block. I didn't write the 1s1 that relates to where hydrogen was. So this electron configuration would be enormous if we did that for every single element. So what we end up doing is consolidating them when we fill a sublevel. That's why knowing the width of our sublevel boxes on the periodic table is really helpful. The S block is only 2 wide. So when you've gone through it, you can put like 1s1, 1s2, I'm sorry, 1s2 reads on the screen. You filled that section. You don't write each individual block. Okay, we just write it when we've completed it. 2s1, we can't complete it because the first block there is lithium where we need to go. So that one is not complete for that reason. It becomes a little easier to follow as we get into bigger elements. You can really see the process. So now we're going to go to the P block, which is located on the right side. And so let's take a look here to neon. All right, neon's atomic number is 10, so we need to have 10 electrons. Sorry, the animation here is in slightly different order than I wanted, but we're working with it. So again, what we need to do is account for 10 electrons. And so if you look at the circles here for these exponents of these superscripts, and we add them, 6 plus 2 is 8 plus 2 is 10, I've accounted for all 10 of neon's electrons. Now, how did I get to this configuration? The period where neon is in 2. So that's the maximum energy level that neon will have. But it's in the P block of the periodic table, okay, on the far right. So because it's in the P block, that tells me I'm going to end there with my configuration. So the way this is read is 1s2, 2s2, 2p6, and you should be on neon. Now let's go to the periodic table here. Again, I have to move myself down, and I'll show you how I read this left to right as I did neon's configuration. Okay, starting at my entryway at hydrogen, I have to start here. So I'm going to say 1s1. Read it to the next one, 1s2. It's full, write it down, 1s2. Drop down to the next period. Now it's new, so I have to start a new part. 2s1, 2s2. I need to keep going. I filled this section so I can write that down. I've gone through 2s2. Write that down. I'm going to continue in this period, and I'm in the P. This is 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. We're on neon. We've completed this section, but more importantly, it's where the element is that we're going to stop. We said this area was 2p and the 6th block in, so that's why we wrote, I'm just going to back up a second here. Okay, so that's why we wrote all of this configuration you see on the screen. 1s2, we went through that section. There's 2 electrons that live there. 2s2, we went through this section. 2 electrons live at that location. And then 2p6, there are 6 electrons total at this location. Altogether, all 10 electrons of neon have an address. Okay, so now let's go to period 3. We're going to talk about magnesium next. So notice magnesium is atomic number 12. So we just have a few more electrons than with neon, right? 2. So we're going to say 1s2, 2s2, 2p6, 3s2, and then we're on magnesium, right? The second block in the S of period 3. You're landing on magnesium, so you're done. What should we be able to see? Looking at all of the superscripts, we should be able to add them and get the atomic number. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, magnesium's atomic number. This is the configuration for magnesium. Okay, let's keep going. All right, so now we're going to go to the P block. Sorry, that's, again, my picture. I don't have a home to have myself stay. So the P block again, but now we're in period 3. So let's talk about argon. So argon is atomic number 18. So the first step, let's find where we're going on our map, right? So we're asked about argon, find it on the periodic table. Note the atomic number. You have 18 electrons to give addresses to. Okay, we're always going to start where we have to, add hydrogen, and count. 1s, you have 2 blocks you're going through. We're going to write it down. It's full, 1s2. Done. 2s2, we're going to fill it. We're going through that section, so we write it down, 2s2. Next, we're in the p block. We're going to fill it. So there are 6 there, 2p6. We record it. We write it down. Now we're dropped down into period 3. To get to argon, we have to go through the S block. I'll bring my periodic table back. Okay, so here's what we've done. Sorry, I'm trying to center it. It's challenging. Okay, so we've done 1s1, 1s2. We completed it, wrote it down. Then we dropped down to the next period. 2s2, I have to go through, so I wrote it down. Then I keep going. 2p6. I'm not at argon yet, so I need to go through 2p6. It's full, I write it down. Drop down to the next energy level. We're at 3 now. 3s2, right? I keep going across. Now I'm in 3p, and there are 1, 2, 3, 4, 5, 6. Now I'm on argon. That's how I got this configuration you see on the screen. Now, what should we be able to do with all those superscripts? We should be able to add them and get 18. And we do. All right, you think you're getting the idea of how this goes? So the problem becomes where we need to go next. As you can see, something weird happens now that we've got the transition metals here. That's our D block. Look at what happens to the energy level. We're starting it with 4s, that's expected. We're in the 4th period. But once we get to start this D, the energy level dropped down a number. This is 3D after 4s. Then take a look. We go through the D, there are 10 here, and we end up with 4p, which is what we expect, right? It's the p block. But we jumped back up to energy level 4. What's going on? Okay, so with these elements now, we're much larger. And so you imagine all of these sublevels, right, that I showed you before. The S is a sphere, right? So we have these taking part. We have P sublevels. Okay, remember the pictures of all of them. They're all overlapping each other when you get this large with these electrons. You've had so many different pieces come together now that we have some overlap. Okay, an energy level is just that. It's measuring the amount of energy the electron has based on its distance with the nucleus. Okay, as these different shapes overlap, and you'll recall D was very complex looking, it's going to overlap with major energy levels. And that's what we see here where it's flipping the energy level number. So the reason it goes from 4s to 3d back up to 4p is because those levels are overlapping in those spots. The atom is just bigger. If we take a look at the very bottom here, where our inner transition or rare earth metals are, you'll notice that for that period, again, looking at where these piece up into the periodic table, they come in right here after 6s. So we're going to go in numerical order. We'd have 6s2, then 4f14, then 5d. So it gets really complex. I rarely ask questions with F because of that flipping around, and it's just kind of, overkill at that point. So don't stress over the F's. All right, here's some practice for you all. So now that I've walked you through, go ahead, give the video a pause, take a look at that periodic table of yours, and see if you can come up with electron configurations for these three elements. Okay, so hopefully you've thought this through and we can go over those configurations. Let's take a look at them. So beryllium is element 4, and so its configuration is 1s2, 2s2. Nitrogen is element number 7, so nitrogen's configuration is 1s2, 2s2, 2p3. And lastly, aluminum is element number 13, so its configuration is 1s2, 2s2, 2p6, 3s2, 3p1. How'd you do? I also want to point out here, now that we have a larger configuration to look at, notice that the configuration, how it's written there are no spaces. The 3 for the energy level is written there at the end. There is like a space shown there. I see that shouldn't be there. So they run right next to each other is what I'm trying to say when you write these. It's hard to show through the computer. Okay, so now we can talk about those electrons spin. Okay, and so when we get into this detail, we're going to look at the 2 electrons that are in the s. We're going to look at the 6 electrons that are in those p sublevels. Okay, what you see on the far right is a diagram that's used to help you remember the filling order. Okay, this is included in one of the periodic tables that I've included with these notes, and so you'll see it on the second page for one of those files. It's right here. All that is, it says cheat sheet here. I won't let you use this, but it's just a way to know 1s2, 2s2. It's an older way to look at this because honestly, reading the periodic table left to right does the job, and it's not as confusing as this looks. So take it what it is. But now that we're going to look at the individual electrons and what they're doing, we have some rules that we need to follow when doing this because the electrons are in different spin and we have to keep them at the lowest energy possible. This is called the Aufbau principle. Now, this is not a scientist. This is either a Latin or a Greek term. I forget those details, but what it means is building up. And so we're building up from the lower energy level and going up to higher energy levels. That's called the Aufbau principle. You need to know this. The Pauli exclusion principle is named after Wolfgang Pauli, which you see his dashing picture there. And so the Pauli exclusion principle says that one orbital, okay, to get your bearings right, one orbital is, if we look at the P example, the P sublevel, it's one plane. So one orbital here would be the x-axis, for example. The entire sublevel for P is made up of x, y, and z. One orbital would be the z-axis. There are 2 electrons that live here. Another orbital would be the y-axis. 2 electrons live here. And lastly, the x, and there are 2 electrons here. So we can say that the p sublevel has 3 orbitals to it. Each orbital holds 2, and they have to be opposite spin. Okay, so that's what the Pauli exclusion principle states. You need to know this. And lastly, we have Hund's rule. This is named after another scientist, okay? And I'm showing you the picture of a bus. That's for a reason. I'll get to that in a second. Let's read the book's definition first. When electrons occupy an orbital of equal energy, meaning all of the p's, okay? So if this were 2p, they're in the same energy level, and that means they have the same energy. Okay, so if we're looking just at the p sublevel of 2, okay? Hund's rule says that as you put individual electrons in here, they all pair in the same direction, then they pair up as opposite spin. Okay? Now, why am I showing you the picture of a bus? Because this is a relatable thing that, that we can relate with Hund's rule. So notice the seat pattern on this picture of the bus that I chose. It's 2 seats next to each other going all the way back. Okay? Now let's imagine you're stepping onto this bus and it's almost full capacity. Let's say there's a couple seats that are empty, but then all the other seats have at least one person. Of course, they grab the window seat, right? What are you naturally going to do? Okay, now if you say that even though there's 2 seats that are empty down the end of the bus, but you're still going to sit next to somebody, knowing there are 2 open seats that are next to each other down the way, you're one of those crazies. Who's going to do that? Okay, be real. You are going to choose a seat where you can be comfortable, quiet, so on. In other words, you don't want Bethany here bothering you when you're trying to get your work done, right? Chewing your ear off the whole time. Nobody does that. We want our own seat. Look at this picture. Everybody's sitting 1 to a row, and we're content. We're able to take a nice refreshing nap. That's Hund's rule. Electrons will pair up this way first, then if they have to sit next to someone, they will. And now you'll remember Hund's rule. So these 3 definitions, Aufbau, Pauli exclusion, and Hund's rule, have to do with the detail we're going to get into now. What you see here is part of an orbital diagram. I call these Aufbau diagrams as well, so you may hear me say that. Okay, we're going to look at one orbital as a square or a box. So again, I'm looking at an orbital of a sublevel. So of P, we can think of this is representing the y-axis. It has 2 electrons. Each box is an orbital, so each box can only have 2 electrons in it. Okay? This is the 1s box, and so the s can hold 2 electrons. You saw that by reading the periodic table, right? Looking at the blocks color-coded on the periodic table. And hydrogen only has 1 electron. So this is what the orbital diagram for hydrogen would look like. Now, does it matter if you drew that electron facing up or down? No, because it's only 1 electron. So you want to be different? Go ahead, draw it down. Okay. Usually the first electron drawn is pointing up. It's just a style thing. If you want to be different, go for it. Okay. The other thing I want to point out to you, notice that this arrow is not a complete arrowhead. It's a half arrow. Okay. That's the designation for a single electron. Okay. So just having that one end of the arrow tip, that's how we draw 1 electron. You'll see what a down looks like in a second. So let's go down to example 3 now in your notes. We're going to do an orbital diagram for phosphorus. Yeah, I'm really kicking it up, right? We went from hydrogen to phosphorus. Let's go. And so we need to account for all 15 electrons. Okay, I hope this animation works. This is my Aufbau diagram, or orbital diagram. Okay, I've included one copy of this as well that I made many, many years ago when I was learning this. with an old word processor because they didn't have computers yet. Bear with me. There was a time. So you'll see that it's typed out. And instead of boxes, I just have dashes, but it still works. And so there are 2 copies on that paper. So anyway, here's where we can practice one. So we want to go in the same order that we did reading the periodic table. That's the Aufbau principle. We have to start at 1s. So we're doing phosphorus, right? So we're going to place 2 electrons. Notice that these electrons have the complete arrowhead. I'm sorry if that's confusing. That's what I was able to use with this animation. Just know when you're drawing these by hand, they are a single arrow side. Okay, sorry if that's confusing. Just going with what I can go with here with Word. Okay, so anyway, so we have them facing opposite directions in 1s. That's 2 of the 15 electrons I need, right? We are doing phosphorus, right? Yeah, okay. So for the next step, it says 11 more because we're going to do the next one. I think this one I was going to do live, if I remember. So give me 1 second. Let me escape. I think how I designed this was, yeah, I was going to drag these over. So here's 2s1, and then there's 2s2. Okay, so we have 11 more electrons we still need to plot. Notice how these are scattered. That's on purpose so that I'm going in increasing order. So after 2s is 2p. So notice that in this Aufbau diagram, the 2p is after 2s but before 3s because that's the order it fills. And so you'll see this zigzag. And then when we get to the D, right, we're going to fill it. It's kind of squished because of making it fit on the page, okay? So 4s is first, then 3d, then 4p, right? So it's going to go that way. Okay. So next, sorry, this is, kind of messy, I suppose. We go to the next slide this way. Okay. We're in a P sublevel now. Notice the 3 boxes for the 3 orbitals. Watch how I put these in. 2p1, 2p2, 2p3. I'm not done yet, but I want to pause here. Okay, this is Hund's rule. See how in the P, or we couldn't do it before because there was only S's, right? The electrons are going to fit in an empty seat first. If that option is there, then as we have more electrons to fit, they have no choice but to sit next to another electron. See? Okay, 2p5, and then finally 2p6 would go in that last orbital. So if I just click off to the side here, that is what it looks like when you complete the 2p. They're in opposite directions, but notice when I was filling it, I put 1 in each orbital in the same direction first. Okay? If we weren't completing this area, this 2p, we would leave it with, all or some of them just pointing in the same direction with 1 to a box. But we're not done yet. Let's keep going. Okay? So again, this is the orbital notation is what we would call this. You get the terminology of, if I ask a certain thing, if I ask electron configuration, I want what we did before, which is listed down here at the very bottom in bold. If I want the orbital notation or Aufbau diagram, I mean the arrows. Okay? So now we have, after 2p, we've got to do 3s, right? 1 of each. Okay, so right now I'm going to check where I am, even though it says over here, 1s2, 2s2, 2p6, that's 10 electrons, 3s2, that's 12. Okay, so next we're going to go to 3p, but again, Hund's rule. Okay, and through the magic of television, we flip one of those like that. and slide them right there. Okay, and so there we have the orbital or Aufbau. You're probably going to hear me say Aufbau more because that's how I learned. But anyway, the Aufbau diagram for phosphorus. All right, back to the slideshow. Okay, so this slide shows what the box is telling you on this particular periodic table that I included with the notes. And so in this box, you're seeing how many orbitals are in a sublevel and how many electrons are maximum for that space. And so you can pause the screen here and take a look at that. The periodic table that I included for you already has it filled out. Just, take this in for a second. All right. Of course, there are exceptions to this rule, right? So let's talk about when this occurs. Find chromium on your periodic table. It's a transition metal. Okay, so you would expect that from where chromium is, this would be the configuration. 4s2, 3d4, right? But if we talk about low energy to high, Aufbau principle, something weird can happen here. I'm going to remind you that at the 4 level where we have the D come in, how it flips energy levels because they're overlapping. Okay, so if they're overlapping, there's an option for that electron to go to the lower energy. And so this is expected. However, this is the actual true configuration for chromium. You spot what happened? Look at the end. One of the electrons that was in the 4s jumped over to 3d. Why would it do that? The 3d is a lower energy level. The first number is the energy level, right? So 3 is lower than 4. It's more stable, energy stability, low energy, think calm, think non-reactive. The D is half full with 5 electrons. That's more stable than having it less than or greater than half full with the 4 in this example. So this is what happens. 1 electron will be donated back so that that larger sublevel is half full. That's a more stable arrangement. Another example that does this is copper. So find copper. It's also a transition metal. And what do we have here? You're going to expect, based on where it is, that you're on 3d9, right? 3d10 would be zinc, but you're one before that, so that's 3d9. But we have a similar situation here, right? The 4s and the 3d. So what happens here is we're so close to being full for 3d that it's going to take an electron from 4s and fill that 3d with the 10 electrons. Okay, so this is when you're in periods 4 and low and higher, period 4, period 5, and so on, because we have that flip over with the D sublevel. This occurs. It will not happen earlier than that. All right, what about ions? We can write an electron configuration for an ion because we know that ions are when you have more electrons or you remove some electrons. So we can show that with a configuration. And so let's take a look at how that would look. So first, I want you to pause the video and write down in your notes what the electron configuration would be for the following elements: sodium, phosphorus, iron, and oxygen. All right, so you've taken some time and written out the configurations for these elements. Let's see what you got. So here's sodium, phosphorus, we did that one earlier, iron, and oxygen. Okay, Make sure that you've added up all those superscripts so that they equal the atomic number for that element, right? That's your check. Okay, so we have to talk about ions again. Refresh your memory. Why does an ion form? Again, I'm going back to the word stability. So the atoms want to be unreactive. They want to be stable, low energy. And so to do that, they want to be like a noble gas, which is 8A. 8 was that magic number, exception helium with 2. 8 was that magic number where the energy level is full. Now you're kind of seeing that picture show up as to why and how that 8 becomes 8. Past that, okay? This is a stability number where the electron energy levels are full. So to be an ion means to either gain an electron or get rid of some so that you attain the configuration of a noble gas, because that's stable, right? So sodium would love to give up this one electron that's the furthest from its nucleus. It's not hanging on to it very tightly. It's way away, right? So it could easily give that electron to some element that needs it, like a chlorine, okay? So if it gets rid of that, what's left for sodium? It would become a plus charge because it lost an electron, and it would have the configuration of, drum roll, neon. Sodium is here. If it loses that 11th electron, it's going to have 10, which is the noble gas, neon, which comes right before sodium. This is a pattern. Let's look at phosphorus. Phosphorus would love to unload these 3 electrons right here so that it can have the configuration of a noble gas. Add to it, I'm sorry. It would love to add to these 3 electrons to get 6. And so phosphorus does that. It becomes a -3 charge. And so adding those 3 electrons pushes the configuration out. So now phosphorus will have the configuration of argon. Next, we look at iron. Okay, iron, let's take a look where we are here. We're unloading these 4s. If we look at both configurations here, okay, and see what happened, the 4s2 is missing in the ion form. Now I will pause for a second here and say iron is a transition metal. So if you recall, I had mentioned that transition metals can have multiple charges. Iron, for example, can be a +2 or a +3. Those are 2 variations of iron. Okay, the +2 here is easier to demonstrate what's happening here. It's losing the 2 from 4s. That's a noble gas configuration. What happens when it's +3? Well, I think we're going to lose. It might be a domino effect, honestly. I don't recall at the moment, but I can look into that if you really want to know. It's probably going to be a domino effect where it's taking one, bringing it to another energy level, and then that's being taken by something else and so on. I don't recall off the top of my head. And then we have oxygen. Okay, so oxygen has 2p4. It would love to be 2p6, so it just needs 2 electrons to do that, and it becomes a -2 ion when it does. And so that would be the configuration of neon, 2p6. Okay. So now I'm going to show you a shortcut. All right, so all this time you may have been thinking, geez, if she asks me something there in periods 6 and 7, it's going to be a while, right? So again, in periods 6 and 7, those would include the F sublevel, which I mentioned earlier was kind of overkill and unnecessary to do for just getting the skill down. So we would stay probably periods 5 and lower. So to show you this, this shortcut, what we're going to do is notice that the end of each line, the end of each period, we're on a noble gas. So what if we just said start here at that noble gas, the one that's preceding the element we're doing the configuration for? We could say start from here, everything preceding that noble gas is implied, and then take on whatever's left to the element we need. Let me show you what I mean. So if we look at titanium there, I've boxed it in red. Titanium has the previous noble gas of argon. So we can write all of this for a noble gas, regular configuration, full configuration for titanium can be written like this, or I can do the shortcut, which you see on the right. You like that shortcut, don't you? Okay, because it makes it less work, right? So what you have to remember to do the shortcut is, one, I have to give you the directive that I want you to do that. If I don't say write your response as the noble gas shortcut or the shorthand, you cannot do that. That's okay. The second thing is keeping track of what noble gas you use. Okay, titanium is located in period 4, so you go to the noble gas in period 3. It's always the one right before it. Okay, let's try these 3 elements and then we'll be done with the notes. So use the shortcut to get aluminum, potassium, and iron. All right, gave you a few minutes to think this out. Let's see how you did. So with aluminum, what I've done here in this first example is I've written the configuration for neon in red so that you can see that that's being accounted for by saying neon. We're putting it in these brackets. That just is the style, so it's not parentheses, it's a bracket. Okay, so we put a bracket around the noble gas that we're starting at, and then just continue from there. We would need 3s2, 3p1, and then you're on aluminum. How about potassium? That'd be argon, 4s1. And iron? Okay, that'd be argon again, 4s2, 3d6. Not bad, huh? So again, remember, I have to be asking you to write it in that shortcut. Otherwise, you've got to do the whole configuration. Ha ha ha. All right, that's the end of the notes for this section. Take a look at the homework that I've posted along with this, try it out, and of course, message me if you have any questions. See you next time.